On this video, we're going to go over your test solutions. On our first question, we are given a function, and we need to know which of the following would be true. And so let's go through each one. And for the first part, the limit as x approaches 4 exists. So we do need to look at the limit from the left and the right. So if we look at our limit as x approaches 4 from the left, then we are going to substitute in up here of our f of x, and that's going to give us 12 minus 7, which is going to give us 5. And then let's look at our limit as x approaches 4 from the right, and we're going to substitute into the bottom down here, and we're going to get 16 minus 8, which is going to be 8. So notice that this limit does not exist. The limit as x approaches 4 for f of x does not exist. So that's going to tell us a few things here for sure, is that one, that limit doesn't exist. Are we continuous at 4? Well, no, because we have two different limit values, so that can't be it. And then the third one, the limit as x approaches 4 from the right is 8. Well, that one is true. So the only one that we have is true is going to be option 3. Okay, our next problem, a limit problem. We're always going to try substitution first. So we're going to have 2 to the 4th minus 16 over 2 squared minus 2 and then minus 2. So that's going to give us 16 minus 16 all over 4 minus 4. So we're going to get 0 over 0, which means we need to factor and possibly cancel. So let's go through and see what's going to happen there, factoring and canceling. In the numerator, it looks like we're going to have x squared minus 4 times x squared plus 4. And then in the denominator, we have x minus 2 times x plus 1. And it still doesn't look like anything's going to cancel, but if we will look a little bit further, we can cancel the x squared minus 4's again. That's going to give me x minus 2 times x plus 2. And then we have x squared plus 4. And then in the denominator, we have x minus 2 times x plus 1. And now we see that we're going to have stuff to cancel. And now we go back and reevaluate our limit. And if we do that, we're going to sub in a 2. So that's going to give us 2 plus 2. So I'm going to have 4 times. And then we're going to get 2 squared plus 4. So that's going to be 8. And that's going to be all over 3. So 32 over 3. Okay, our next problem, again, we are still substituting in. So when we substitute in with this, we need to see what we're going to get here. But we're going to end up with the square root of 3 minus the square root of 3 over 3 minus 3. So we are going to get 0 over 0. So now we need to do our rationalizing for this one. So we have the square root of x minus the square root of 3 over x minus 3. So we need to multiply the top and bottom by the square root of x plus the square root of 3 over the square root of x plus square root of 3. And so when we multiply this all out, we really ended up just multiplying the first and then the last, because those middle terms do cancel each other out. And then in the denominator, we do bring over our x minus 3. And now notice that we are where we can go ahead and do some canceling here. And so now we can go back and redo our limit as x approaches 3. And we're going to have this as 1 over root 3 plus root 3. And that's going to give us 1 over 2 times the square root of 3. So now let's see. Oh no, it doesn't match. We're going to have to rationalize. So let's go back through, multiply top and bottom by root 3. So that's going to be root 3 over 2 times 3, and that looks like it's going to be A. Okay, number 4, notice here that our x value is approaching infinity, and so that means that we are definitely going to have what we call a power struggle. That's what this problem is going to become, and that also deals with a horizontal asymptote for sure. So let's take our highest power that we see in the numerator. That's going to be our term that has 3x squared. In the denominator, it's going to be x cubed. And notice that the power is going to be in the denominator. So as x grows without bound, this entire fraction is actually going to approach 0. So my answer here is C. Okay, for number 5, again, looking through this, we are approaching negative infinity, so we're back to a power struggle again. The highest power I see on top is 5x. The highest power I see in the bottom, well, that's going to really just be the square root of x squared. And we need to remember that that really becomes the absolute value of x, not just x by itself, it becomes absolute value. And now looking at this, we do still have our power struggle, but x is approaching negative infinity. So notice that we're going to have 5 times a negative big over the absolute value of negative big. And so here we're going to have a negative 5 times big over just a positive big. And notice this is tending toward negative 5. All right, so now we're trying to figure out where in the world are we going to be continuous everywhere. And this is where we need to go back and look at our limits. And so notice that our question here is round 2. So let's look at our limit as x approaches 2 from the left of our function, which is going to be this numerator here. So we're going to plug in there, and notice that this is going to end up being 2 squared, which is 4, plus c squared. And then on our other side, we have the limit as x approaches 2 from the right of g of x. And that, if we sub in, is going to be 5c minus 2. And now in order for this to be continuous, our limits have to exist, and those limits have to be set equal to each other. So for this one, we're going to set 4 plus c squared has got to be equal to 5c minus 2. And if we go ahead and rearrange this, we have our c squared minus 5c, and then we're going to have plus 2 equals 0. And so this turns into a nice factoring problem. And so if we factor this, we're going to end up with, move my screen over, we're going to have c minus 3 times c minus 2. I see what I did. That should be a 6 there, guys. Okay, and all of that equals 0. And so we're going to get c to be 3 and c to be 2. So that's going to be answer choice A. Right, so a good review question in number 7. And here we have the graph of f of x is reflected across the x-axis and shifted up 3. So reflected over the x-axis, so that means I've multiplied on the outside. And then I need to move this up 3, so I need to add 3 to it. So that's going to be answer choice D. All right, so on number 8, for this limit to be true, so the limit as x approaches 4 of f of x equals 9, which of the following must be true? Well, We don't have to be continuous at 4. We could sketch this and see that, just make an open circle here, make this at 4, and make this limit here, let's see, at 9. Notice we're not continuous, however, our limit does exist. F at 4 equals 9, that doesn't have to be true. And f of x is defined at 4, that doesn't even have to be true. So none of those things have to be true. All right, number 9. This one was a pretty tricky problem here. It was kind of tough for us to see. We have the limit as theta approaches 0 of x times cosecant of x. Now, when we plug in, notice we're going to get 0 from that first x times, now cosecant of 0. Now, we have to be careful with this because cosecant of 0 is really undefined. That's the same thing as 1 over sine of 0. And so that's going to give me 0 times undefined. And so we don't know what that's going to be equal to. So this problem, we needed to go back as theta approaches 0. And let's rewrite this. That's going to be x over sine of x. And again, that's because cosecant is 1 over sine. And for this one, this limit is one of those special limits, and it is always equal to 1. If you'll look back on your notes, it is on that first page of limits analytically that we looked at. Okay, number 10, we are going to sub in, and again, we're subbing in a negative infinity. So let's look at what happens here. I've got 2 raised to the negative x, but in place of x, I'm putting negative big over 2 raised to the negative big. Okay, so let's work out these rules. We've got this negative times this negative, so that's going to be a positive. So I have 2 raised to the big. And then notice this negative exponent is going to flip this over. So that's going to be times 2 to the big. And so now notice that as x increases without bound, this whole thing gets really, really huge. So this thing is approaching positive infinity. All right, number 11, again, we need to substitute in. So I'm going to have 2 times sine of pi over 2 over pi over 2. That's going to be 2 times 1 over pi over 2. And so remember, that's the same thing as saying 2 divided by pi over 2, which is going to be 2 times 2 over pi. And that's going to give us 4 over pi. Okay, so for our next problem, we're looking to see this limit value, and we're going to have to use our 2 graphs in order to do so. So we have the limit as x approaches 2 of f of x, and then minus 3 times g of x. So with our limit properties, let's see, what is the limit as x approaches 2 for f of x? So looking up here, the limit as x approaches 2, looks like it's going to be a 1, and then we have minus 3 times, and now the limit as x approaches 2, over here at g of x, it looks like that's going to be right inside here, so a negative 1. So we're going to get 1 plus 3, so it looks like we're going to have 4. Okay, for number 3, the limit as x approaches 1 from the right of just 3 is still just going to be 3. Nothing we can do with that. Minus the limit as x approaches 1 from the right of g of x. So the limit as x approaches 1 of g of x from the right, coming in here, looks like it's going to be a negative 1. So again, it looks like here we're going to get that times a 3. So we have 3 and then minus a negative 3. So that's going to give us 3 plus 3, or 6. Okay, number 14. The graph of f of x is not continuous at x equals 0 for which of the following reasons? So at x equals 0, we're not continuous. Why? Well, let's look and see. At the first part, and we're talking about f of x, so we're on that function. F at 0 is undefined. Well, we know that's not true because you've got that point there. So it can't be for choice 1, and so I'm going to mark out anything that has choice 1. Now let's look at choice 2. The limit as x approaches 0 of f of x does not exist. Well, we know that is true for sure. And then notice number 3, the limit as x approaches 0 of f of x doesn't equal f at 0. That one is also true. However, this limit is not existing. So that one's kind of strange. We could have taken both B because you couldn't even really talk about that limit, but really B or C here could work. All right, our free response question, the first thing we needed to do was to find this limit, and we had to show our work. And so really all we're doing is subbing in that -1. So we need to look at f at -1 times 3 cosine of pi times -1. So over here to the side, we've got to go find f at -1. So if we substitute in, we're going to get 2 minus 11 plus 5 all over, and plugging in -1 in the denominator is going to be 1 minus 1, and then minus 20. And so in the numerator, it looks like we're going to get -4. In the denominator, -20. So that's going to reduce down to positive 1/5. So I'm going to come back over here and have 1/5 times 3 cosine of -pi. And so with -pi, that just means we're going to go this way, and we're going to get the same exact answer. We're going to have -1. So I've got 1/5 times 3 times -1. So that's going to give us -3/5. Okay, so here on the other part, we've got to talk about any vertical asymptotes, and that's going to be where this denominator is 0. Now, something very important here, we need to factor the top and bottom. So let's see what f of x is going to look like. In the numerator, we need to factor that, and we should get a 2x plus 1, and then an x plus 5. That's going to give us 10 and 1, so that'll work. And then in the denominator, we're going to get x plus 5 times x minus 4. Now, notice these are going to cancel, and so what's left over is 2x plus 1 over x minus 4. And so your vertical asymptote is going to come from this denominator, so we're going to say x minus 4 equals 0. So x equals 4. Now that's our vertical asymptote. And to justify this with our limits, we're going to say that the limit as x approaches 4 of f of x does not exist. And the reason why it does not exist is if I plug in 4, I'm going to get 9 over 0. Now, another way you could do that is to sub in here and look at it from the left and the right. The limit as x approaches 4, and I'd much rather y'all do this way and approach it from the left and the right. So from the left of our function, so if I plug in something smaller than 4 into that x value, then I'm approaching negative infinity. And then if I look at my limit from the right side, as x approaches 4 from the right of our function, if I plug in something bigger than 4, then I'm going to get a positive infinity. And those two together, working together, is why our limit does not exist. Now state any horizontal asymptotes and use limits to justify. So we saw our factored form, And you don't have to use your factored form here for the horizontal asymptotes. However, it's a good idea. We saw that f of x from the previous problem reduced down to be 2x plus 1 over x minus 4. And so with our horizontal asymptotes, that is always talking about our power struggle and our limit as x approaches infinity of f of x. So if we look at that, then we're going to isolate the highest term on top and the highest term on bottom, and notice that generates a 2. So this would be it. There's your horizontal asymptote. It's at y equals 2, and we justified it with our limit. And finally, this last problem here, again, it's very similar to our previous one. We see that x is approaching infinity, so we need to talk about any asymptotic behavior. And that's really here, if x is approaching infinity, that's going to be our horizontal asymptote every time, if there's one there. So what we need to do here is pull this down and just look at our power struggle from that. So in the numerator, I have 5x squared. In the denominator, I have the square root of x squared. And again, that's going to be 5x squared over the absolute value of x. And so notice that that power struggle is really going to be maintained in the numerator. So notice for this one, as x approaches infinity, as x increases without bound, then f of x here, or that limit, or I'll just go back and call it, was it f of x? No, it wasn't. Let's go back and just call it what we've got it to be. Then our limit, 5x squared plus 3x over the square root of x squared minus 4x, here becomes unbounded. In other words, it is going to grow without any kind of bound, becomes unbounded, and so therefore there's no asymptotic, fancy word there, behavior.